In this video, we are going to review some of the most important calculations you will need to know for the NAPLEX, and we are starting right now. Hello, this is Dr. Dankwa, and if this is your first time here and you like to learn pharmaceutical calculations, tips, tricks, and strategies, then start by subscribing and clicking the bell so you don't miss anything. Now, this video is from a NAPLEX calculations review session I did for my students at the College of Pharmacy where I teach, and we covered TPN calculations, milliequivalence, osmolarity, and dilution, and I'm sure it's going to be beneficial for you as well. Now, if you want a review session that looks like this, just send me an email at info@RxCalculations.com. But let's get right to it. Okay, so I think the format we will use is I put the question on there, you give it a quick attempt, and then we digest it together. We'll be looking more at TPNs, some milliequivalent calculations, and also some of the compounding calculations. So this right here is, you could solve it using proportion or dimension analysis. I normally recommend dimensional analysis, but if you want to use proportion, that's fine. So once you've gone through it, we can just simply do it together and identify any opportunities for reinforcement. Let's go ahead and do this together. So what we have here is a 45 milliliter nasal spray, and it delivers 20 sprays per milliliter of solution. Each spray contains 1.5 milligram of active drug. How many milligrams of drug are contained in the 45 milliliter package? Does anybody have an answer for us?
1,350.
Yeah, I see that, and that's correct. Now, how did you solve this? Did you use proportion or did you use dimensional analysis?
I use dimensional analysis.
Okay, so let's proceed with that. So the question here is asking for quantity in milligrams. Now, typically, just to recap, the reason we want to start from here is you need this dimensional analysis, ratio, and proportion for the other calculations as well. But the real trick is understanding what is going on in the question. Now, since we are looking for milligrams, we have information on the sprays, number of sprays per milliliter. We also have the volume of the nasal spray, and then we have the quantity in milligrams that each spray contains. So we want to combine all of those together. So you have 20 sprays per milliliter, and you want to multiply this by the volume. So just to recap, your volume is 45 milliliters. The milliliters go away, and the way the dimensional analysis just works is you cancel the numerator to denominator, right? So at this point, we need to be in milligrams, and that's where this conversion factor comes in. So you always have a conversion factor that takes you from where the information you have to where you need to be. The conversion factor we have now is 1.5 milligrams per spray. So the sprays cancel out. And if you're doing this, the next step is to multiply all the times in the numerator. So you have 20 times 45 times 1.5 milligrams divided by 1. And that should give you the 1350 milligrams. So if you got this, that's fine. If not, this is just a review. And the important thing always is to identify what we call your conversion factors. In this instance, you have 20 sprays per milliliter, and the sprays, how much the drug actually contains in each spray. So how many milligrams of drug are in each spray. So that's the first one. This is just like warm up. So for TPNs, let's start off with what do we need to know for TPNs? First, you need to know your conversion factors. In addition to knowing the conversion factors, you need to be able to understand or memorize or know what the Harris-Benedict equation is for males and for females. Sometimes they do ask that. Then you need to know the following, okay? So if I have a 10% lipid emulsion, how many kilocals are in a milliliter? Those conversions, you also need to know that. Aside that, I think that's everything you should probably have stenciled on your mind, and with that, you should be able to solve every other question. So we're going to start off with a TPN question, which at this point, based on the feedback I got, you have the requisite information to do this question. And then let's debrief about how to approach this type of question. This is a type of problem, okay? You will see it for phosphates and for acetates. And so what you need to do is know how to handle these types of problems. Create like a shelf where you know when I see this type of problems, what I need to do. All right, so let's discuss this. Let's talk about what the question is asking. So here we have PN, and PN contains, that's your TPN, right? It contains 6 milliliters of potassium phosphate, right? Now, this potassium phosphate has 3 millimoles of phosphate and 4.4 milliequivalents of potassium in each milliliter. And normally on even on the NAPLEX, I'm quite sure that they will give you that information. So you don't need to memorize that piece, okay? So here it says the daily potassium requirement from the TPN order is 40 milliequivalents. how much potassium chloride with a concentration of 2 MEq per ml in milliliters should be added to the PN round to the nearest tenth. So what I try to do is basically highlight or underline all the information I think is important. Everything else is words, right? The question is, where do you start? What's your strategy? So sometimes we want to know what we are looking for. So we are finding, and I will erase all of this soon, we are finding volume in milliliters. That's this question. Volume in milliliters of potassium chloride. So if that's the case and we have all the information, what's the problem? We need to figure out where to start. So where to start is anytime you have a potassium phosphate situation and you are being asked to find like the volume of potassium chloride to supply your potassium required, you need to figure out how much phosphate the patient already has. Let me just go back one step. In this question, they told you the volume that was already given. Sometimes they don't tell you that. They just give you the amount of phosphate. So maybe the patient has 30 millimole of phosphate. You need to figure out how much of the solution will give that 30 ml. And then that volume, in this example, the 6 ml, also contains some potassium. It is potassium phosphate. So the strategy is in your step number 1, determine the amount of potassium that accompanies the phosphate. If you want to write this, maybe it's a good idea to write that down. So the way you would do that is you take that volume. In this question, it's been given to us. Sometimes you calculate it by determining the volume to get your millimolar, and then you multiply that by this conversion factor. So you have 4.4 milli equivalents of potassium in each milliliter, and you're given 6 milliliters. Okay. You could also do a proportion. I just did a dimension analysis. So what that means is by taking the 6 ml, you're also given essentially 26.4 milli equivalents of potassium. It's only basically a 2 or 3 step strategy. First, figure out the potassium that accompanies the phosphate. Then in step 2, you do an accounting or a subtraction. So in step 2, you take the total that the patient needs. So the patient needs 40 MEq, and you subtract from the 40 or your total the potassium quantity that was accompanying the phosphate. If my math is correct, this should be about 13.6 milliequivalent. Now, that's not the answer. This is what the patient needs. This is how much already accompanies the phosphate. So you're going to use this potassium chloride to supply the 13.6. So your third and final step for this type of problems is you take the conversion factor here, or the concentration actually, which is 2 milliequivalents in 1 milliliter, and figure out if I have 13.6 MEq, what volume should I give? You see that?
6.8.
All right. So if you got 6.8, I think it looks reasonable. That's correct, right? So X equals 1 milliliter times 13.6 MEq divided by 2 MEq. And this gives you 6.8 milliliters. So if you just follow this thought process, you would always get the answer correct. I promise you. Okay. So the one thing that this question doesn't really ask from the beginning is how they got the 6 ml. So say, for example, you wanted to give this patient, let's say they didn't give it a 6 ml, but rather said this patient needs 18 millimolar of phosphate. Then what you're going to do is you're going to take this 18 millimolar and divide it by the 3 millimolar per liter. And that will give you 6. So this question kind of took that first step out and told you exactly what volume to take, right? So I picked the 18 because it's going to give you 6, but let me use a different number. Let's just say, let's make an auxiliary question. Let's say you need to supply this patient 35 millimolar of phosphate. My question to you will be, what will be the volume of this potassium phosphate solution that will be needed for this preparation?
Around to 12 whole number.
Actually, I should just make this 36 millimolar phosphate. What would that value be?
That will be 12.
12. Okay. How did we get the 12? You took the 3 millimolar in 1 milliliter, and you need to supply 36 millimolar. So when you solve for y, you end up with 36 divided by 3, and that will give you 12. So to determine if it was the same question, what will happen is to determine this amount of milliliters, wherever you see 6, you would have put 12. Because I'm trying to make sure that we have some, like a cheat sheet of things to look out for, right? By following this process, you'd have covered all the things to look out for. The first thing you look out for is, do I have a volume of my potassium phosphate? If I do, I'm simply going to follow these steps. 1, 2, and 3. If I don't have the volume, but rather I have the millimolar of phosphate, then I need to do this preliminary step, which this should be actually milliliters. You should do this preliminary step, and then that volume you get is what goes in the step 1 here. Everything else follows. So you find the potassium accompanying the phosphate, find the difference, and use the concentration of your potassium chloride to find the volume that you need. You can't beat it. That's always what's going to happen. Let's kind of change gears a bit to give you a slightly calmer one. So here you have TC, who is 50-year-old, receiving 1,000 milliliters of D70W and 700 ml of 10% amino acids and 350 milliliters of 20% lipid emulsion daily. What is the daily amount of calories supplied by the lipids? Okay, so I know most of you are kind of, putting the numbers in there invisibly. Let's talk about what's important in the question. So here was our goal. When you see this kind of question, just jump for joy, okay? Because this is the kind of question that you can do in a heartbeat once you've settled in your mind what to do, right? So we are looking for daily amount of calories. Did we see that? And you have so many, or you've been given a lot of information, but really what's important in the question? The real thing is supplied by the lipids. So we're looking for the source of the lipids. How are you supplying the lipid? You're using a 20% lipid emulsion. That's how we are supplying the lipids. What does that tell us? What that reminds us of is I need to recall the conversion factor for that. And for a 20% lipid emulsion, you have 2 kilocals in 1 milliliter. So you're just going to multiply this by the volume. What's the volume? It is this volume, not this volume, and not that volume. We're just focusing on the volume of the lipid emulsion. So we multiply this by 350 milliliters. That goes away. And you're basically multiplying the 2 kilocals by the 350, and that gives you the 700. Let me ask a different question. Let's say you had 350 milliliters of a 30% lipid emulsion. What would be different?
It looks like 3 times 350.
Exactly. So let's use this as an opportunity to just refresh our minds. There are normally 3 sources: 10%, 20%, 30%. This one right here, we just did this. This is 2 kilocals per ml. This is 3 kilocals per ml. And what is this one?
1.1.
1.1. That's the only one that's 1.1. Yeah, so just memorize this. You can dump it after the exam. I shouldn't say that, but so you need to have this, right? So depending on the lipid emulsion or the concentration, you would change this accordingly. Other than that, you simply need to multiply the volume of the lipid emulsion by that factor. Yeah, so this is a much more simpler one, which is a good one as well. Let's do something slightly involving. Once we cover this, you should be kind of like in pretty good shape. Let's discuss this and then proceed with the solution. Normally, when you get a question, sometimes there are a lot of words, but my recommendation is look for what the actual question really is, right? So what's the question here? What percentage of non-protein calories are represented by dextrose? And the reason that strategy really works is sometimes it lets you kind of go with a laser focus to know what information to go and pick. Because if you read all the question, then you come back, then you have to read again, right? So sometimes if it works for you, just read the question first and then go read the whole preamble. Okay, then that will give you some things to pay attention to. So we are looking for non-protein calories. In this question, what will be the information that is important here?
The dextrose and the lipids.
The dextrose and the lipids. So because it's saying non-protein calories, we are not interested in amino acid because that's the source of protein, which is an amino acids. Now that we know what the non-protein calories are, we need to express the quantity of dextrose, the calories of dextrose, over the total non-protein calories. So having said that, it means that the first strategy will be to figure out, well, how many calories am I getting from the dextrose and how many am I getting from the lipids? And then we are going to add both of them up and then take the calories of the dextrose and divide it by the total. Now, once you determine like a strategy like that, you just know, okay, this is what I'm going to do. So for dextrose, let's talk about dextrose for a minute. How do we find those calories?
First of all, look for the grams.
Yes. So we need to look for the grams. So you could do this, everything in the calculations, you can do either ratio, proportion, or dimension analysis. But either way, the concept is the same. So looking for the grams, what that means is we should know what the concentration is. Yeah, using a D50W. D50 is 50% dextrose in water. So you have 50 grams of dextrose in 100 milliliters. So what we just did is we reviewed percentage concentrations, grams over 100 ml. Now, to find the grams of dextrose, we need to multiply this by the volume that we have. So 1250 milliliters. Now, you notice we just canceled out the milliliters. So the only unit we have here is grams. You multiply what's in the numerator, divide by what's in the denominator, you get your quantity. You could do that and then go through the next step, or you could do the whole thing in one step. Exactly. So we've done this piece to get in grams. What is the information that we need to get from grams to calories? There is a conversion factor to move from grams to calories or kilocals for dextrose. And what is that value? So you have 3.4 kilocal per gram. So this is the factor that we need. So these grams cancel out, and everything you multiply in the numerator, divide by what's the denominator, and that'll give you answer in calories. So for dextrose, it implies that you're going to have 50 times 1250 times 3.4 kilocals divided by 100. And what does this give us? This gives us
2125.
Exactly. What is this 2125? That's the calories supplied by the dextrose. So we haven't gotten to that final step yet, but this is the value that will go in our numerator when we are finding the percentage. So let's do the second part, or I'm just calling the second part, but the next step will be to find the calories from the lipid or intralipid. So let's put here intralipid, and we have a 10% solution. What does that remind us of? The conversion factor that is needed. And what would that value be? Exactly. You guys are on fire, right? Or you are getting there. So now you multiply this conversion by the volume. Once again, it's 350 milliliters. The milliliters cancels out, and you have 1.1 times 350. And I think okay, calculator says 385 kilocalories. Now, at the beginning, we talked about the whole strategy, but let me just ask for emphasis. What's the next step here?
We add the calories.
We add the two. Okay, so we need total calories. And these are for the non-proteins. So we'll do 2125 plus 385, and that's going to be equal to
2510.
2510. And what's our next step?
We look at the percentage.
Find percentage.
2125 divided by 2510 times 100.
So that would imply you take the calories from the dextrose, 2125 kilocal, divided by the total, which is 2510, and then you multiply this by 100%. That gives you, it says round to the nearest whole number, so always pay attention to kind of guidance in the question.
85.
85. Okay, so if everybody go 85, we will trust everybody with that. So let's talk about the important things here. First of all, you need to be able to digest the question. We did that. Strategy, read the question first. I mean, the real question. Then go read the entire thing, so that will let you know where to zone in on. We focus on the term like non-protein calories. It reminded us of percentage concentrations, okay? 50%. Now, if you were using a D70W, this is what's going to be different. So the 50 grams, you have 70 grams over 100. Then if this was different, we already talked about that in the previous slide. It could be 20%, 30%. What's going to be different? Your conversion factor here is going to be different. Now, this is non-protein calories. What if it said, what is the percentage of calories that are represented by dextrose? Then you would include the amino acid as well. What's the conversion factor for proteins from grams to kilocals?
4 kilocals per gram.
4 kilocals per gram. So notice that for lipids, let me make a summary point here. For lipids, you simply take the conversion factor and multiply by the volume. For dextrose and amino acids or proteins, you need to first find grams. So you multiply the concentration by the volume to get grams, and then you multiply by the conversion factor. That's important.
So did we divide the total by the amount of dextrose because it asks the non-protein calories that are presented by dextrose?
Exactly. So we did that for the main reason that is asking for keywords. Let's talk about key phrases. So the first key phrase here was, hey, you need to find the percentage. You need to find the percentage of the non-protein calories represented by dextrose. So that's why we did this. So we had to find dextrose, find the total non-protein calories, and then percentage. So good question.
So if it had asked lipid, then we would have done the opposite?
Yeah, so if we had asked for what percentage of non-protein calories are represented by lipids, then we'll put this value, the 385, at the top right here, and still divide by the total.
Why do we put it at the top? I'm just asking.
No, that's fine. So what it is you're looking for a percentage, right? So anytime you're looking for a percentage, it's essentially asking for a fraction of something, the contribution of something. So you have a huge pie, and in that pie you have, let's say, 6 different quantities. What's this? 1, 2, 3, 4, 5, 6. Yeah, 6 different pieces of pizza, right? So this whole piece is always going to be the total. And so depending on whether here is almost looking like the same, but depending on whether we pick this or we pick that value is going to be different from each other. And so we will always have this total at the bottom, but what goes at the top here is going to be the contribution from the portion that we are interested in, because you are mixing 2 things, and in those 2 things they give you a total of something, and to find the fraction of that thing in the total, we put the quantity represented by that component. So what we could do, that may have answered your question, but let's amplify it some more. If we said we were interested in the percentage of total calories represented by amino acids or proteins, then we have to find the pie just got bigger. It got bigger because we added this to it. So we now also need to find the calories from here, and we'll use a step that is similar to what we did for dextrose. I'm running out of real estate and I don't want to make it too messy, but let's just do that. So new question: what is the percentage of the calories represented by proteins? That's a new question. So if that was a question, we have already done for dextrose and for lipids. Now let's do we need the information for the protein. So I'm going to scroll down just a little bit. Just keep the numbers. This is 380 and that's 15%, right? So for lipids, we have dextrose. Now let's do, this is a new question. So for the amino acids or proteins, let me just do proteins. How are we going to find the calories? We have an amino acid, 15%. Was that correct? So 15% is a percentage strength, 15 grams over 100 ml. We need to find grams first. So we multiply this by the volume. I believe the volume was 380. Yes. So at this point, you are in grams. So if you did 15 times the 380 divided by 100, you essentially have 57 grams. But that does you no good until you convert it to calories. So your calories, you're going to use that conversion factor we talked about. There are 4 kilocals in 1 gram. So the grams go on away. So 57 times 4 gives us 228 kilocals. If everybody got that, I think my calculator is working. So this is the calories from the protein. This value will go in our numerator, but what it means is we need to determine the denominator again, right? So in this case, we are calling our larger pie still total calories, and it's going to be 2125 kilocal plus 385 kilocal, and the 385 is from the intralipids plus the protein, right?
2510.
Yeah, I could have just gone here, right?
Oh, okay.
Yes.
Okay.
But some people will want to find out where the 2510 came from, right?
Okay.
So let's but you're right. So you could simply take this one and add that to 288, and that should give plus 2510.
2378.
I have 2738.
Yeah, 2738.
What was the question? The new question, the part revised edition of the question. What percentage of calories represented by proteins? What you do now is you take the parts of the protein or the contribution of the protein, which is 228. You divide that by the total, and then you multiply by 100 always. So 228 divided by 2738 times 100 is actually, I have 8.33. I believe it said round the nearest whole number, so that will be 8. So back to the original question, which we kind of sidetrack a bit. You're always going to put whatever you're being asked to express as a percentage, always put the value of that thing at the top. Always. That's your numerator. And then your total is always going to be in the denominator. Your total will vary depending on what the question is asking. If it's asking for non-protein calories, you just don't include the amino acids or proteins. If it's asking for total calories, because that could always happen, like we looked at the second example, then you need to find for everything and add it. So we have reviewed those. What have we reviewed actually? Let me just tell you we've reviewed the conversion factors. Then we've also reviewed the concept that for dextrose and for proteins or amino acids, when you have your dextrose and amino acids, you always need to go through this route. You need to find grams and then use the conversion factor. Always bear in mind what the total calories are. Here, non-protein, we stay here. For total calories, we have everything. Okay, let's do this. First, you read the question, right? What's the real question? Calculate amount of amino acid in milliliters that SH should receive. So we're looking for volume of aminosin. Now let's go to the question. SH is a 55-year-old male. The weight is 220 pounds. He's confined to bed, activity factor 1.2 due to his current infection. So the stress factor is 1.5. SH requires 1.4 grams per kilogram per day of protein, and the pharmacy stocks aminosin 10%. Calculate the amount of aminosin in milliliters SH should receive. Round to the nearest whole number. So once again, based on the question, I highlighted what are the important values or numbers in this question. For this question, we really don't need activity factor. We don't need stress factor. So when we look at this normalized quantity, 1.4 grams per kilogram per day, what that means is we need to have the weight of the patient in kilograms. Now, you could do all of this as a one shot, but just to make the steps clearer, let's talk about the first step. First, convert the weight to kilograms. So we have 220 pounds for the patient, and this reminds us about our conversions, the simple basic things, right? What's the conversion from pounds to kilograms?
2.2.
So 2.2 pounds is 1 kilogram. The pounds cancel out, and so this patient is 100 kilograms. The only reason we did this is because we're going to use that information together with the normalized information here to determine the actual amount in grams per day that SH needs. So we're going to take the 1.4 grams divided by kg per day, and we can multiply that by the weight, which is 100 kilograms. What does this give us? 140 grams of protein per day. This is not the answer yet because it's asking for volume in milliliters of aminosin. How are you supplying this patient 140 grams a day? Are you giving this patient chicken? No. You are basically using aminosin 10%. So the 10% is also going to remind us of percentage concentration. And so what that means is we have 10 grams, right? Protein in every single 100 milliliter. This patient needs to get 140 grams of protein per day. So we can do a proportion. So X is going to be equal to 100 ml times 140 grams divided by 10 grams. The grams cancel out and you end up with 1400 milliliters of aminosin. So for these type of problems, if you are given a normalized dose, well, it's not really a dose, but a normalized quantity, you want to pay attention to quickly what the units are. So since it's in grams, we know that our concentration is going to be grams per something, so we don't need to worry about that, but it's in kilograms, right? So the patient's weight, we need to check to make sure it's in kilograms as well. Once that is all set, you can literally do all of this in one step, but we kind of broke it out into 3 steps to show you the various thought processes that are going on. First, the patient's weight in kilograms. Second, the quantity per day. And then third, you actually find the volume. What could be different here? Let's talk about what could be different. What could be different is depending on the patient's situation, this value could be different, but that doesn't change much. It's just simply some minute figure differences here. The other thing that could be different is the concentration of your source. You could be using aminosin 8.5, 10, 15. That could be different, and that would influence what's happening here. But because you are comfortable with percentage concentrations, it doesn't matter what that value is, you would always set up a ratio that is similar to the 10 grams per 100, depending on the concentration. All right, so let's talk about the question, or let's go through the process. The strategy here is similar to what we talked about for what happens when you deal with phosphates. It's the similar thing for acetates as well. You find the contribution from the acetate, that's the contribution of sodium that comes along with the acetate, and then find the difference and then make up the difference using the sodium chloride. So question is saying what quantity in milliliters of each stock solution should be added to the PN to meet the requirements. So now let's go through the preamble. The pharmacist is making PN that needs to contain 60 milliequivalents of sodium, 30 milliequivalents of acetate. The pharmacy stock solution contains 4 milliequivalent of sodium as sodium chloride and 2 MEq per milliliter sodium as sodium acetate. The final volume of the PN will be 2.5 liters and it should be infused at 1 ml per hour. So now this information, although important, necessarily relevant to our solution. So the first thing we want to do is by giving the sodium acetate, how much sodium accompanies it. Now the first thing though is we need to supply 30 MEq of acetate. So let's do this. Step 1. So you're supplying 30 milliequivalent of acetate. Your solution is 2 MEq per ml. So you need to first find that volume. So you're going to take the 2 milliequivalents per milliliter, and we need to figure out how many milliliters gives us 30 MEq. So here X is going to be equal to 1 ml times 30 divided by 2 MEq. So this is 15. 15 milliliters. Now, this 15 milliliters is the volume of sodium acetate that we need to supply the 30 MEQ. But when you give this 15 ml, you also give some sodium. And although the value is the same, just like it's in the chat box, you just want to go through the entire process. So we're going to take, it's the same concentration. So we're going to take the 2 MEQ per ml. And we're going to multiply this by the volume, which is 15. So it kind of looks redundant. If you were doing this and you had a keen observation, you could simply go straight ahead. But I recommend you go through the process. But this also is going to give you 30 MEQ of sodium. So what we need is to supply the difference. And the difference is going to be, you have 60 MEQ that is needed. You subtract what accompanies the acetate, which is 30 MEQ. So we need 30 milliequivalents of sodium, an additional 30 milliequivalents of sodium. And that's what you're going to supply using the sodium chloride, which has a concentration of 4 MEQ per ml. So in the third step is you have 4 milliequivalents in 1 milliliter. That's equal to 30 MEQ over some volume. So if you solve for the unknown, going to be 1 ml times 30 MEQ divided by 4 MEQ. And that's going to be equal to 7.5 milliliters of the sodium chloride. So the strategy is very similar to what you do for phosphates. You first find the components for the acetate, find that volume, find the sodium accompanying the acetate, which was this value right here. Find the difference. That's how much you need to make up with sodium chloride. And then you use the information on sodium chloride, the concentration, to find the volume. So like I said, if you follow those steps, you will never get a question wrong. Impossible.
So, Dr. Dankwa, will the answer require like 2 quantities, like the one from sodium acetate and the other one from sodium, or is just one answer? Is it just a 7.5, or it requires the 15 mils and the 7.5
It requires the 15 mils and the 7.5 mils.
Okay.
Yes. And technically, this question is saying to the nearest 100, so you may want to add a 0 to it. All right, so we reviewed that, and I feel there's just one more thing on TPNs that we need to do, and then we can move on to something else.
Dr. Dankwa,
Yes.
what did you say about the sodium, potassium, or the calcium? Was that I was trying to figure it out. And what would you use?
Question.
Sodium chloride and sodium acetate. Hold on, let me reword the question, maybe.
Yeah, we read it.
Why would they use 2 solutions here? Is there a reason, or just
Absolutely, there's a reason.
like a sodium chloride and sodium acetate, 2 sources of sodium? Because I sleep off at the last one asking for sodium. Yeah.
So there are 2 sources because each source, let's talk about the sources. You have sodium chloride and then you have sodium acetate. They each have their peculiar and specific purpose. The sodium acetate is solely to supply the acetate, to supply this. Okay, this sodium acetate, that solution is only to supply the acetate, not the sodium. So once you've given the patient the 15 ml of sodium acetate, you have given 30 MEQ of the acetate. Now, if you decided, let's just take a parenthetical detour. If you decided to supply the entire 60 using the acetate, you're going to give 60 MEQ of acetate. Too much for the patient. Not possible.
Got it.
Okay. So use acetate.
Thank you.
Okay, good. So use the sodium acetate to supply the acetate, and the difference, because you still need 30 MEQ more sodium, you use the sodium chloride. Now, sodium chloride has no acetate in it, so you don't change this. That will stay the same from here. But by using a different source of the sodium, like sodium chloride, you're able to make up the difference that is needed to get to the 60. That's why you have the 2 sources. Okay. So this is when you're having calcium and phosphate, those calcium phosphate issues. You don't want any precipitation in your preparation, your TPN. So you always want to make sure that the concentration does not exceed 45 MEQ per liter. So question is asking, determine whether the sum of calcium and phosphate exceeds or does not exceed 45 MEQ per liter. Okay, let's digest the question. So it says determine whether the sum of calcium and phosphorus exceeds or does not exceed 45 MEQ per liter. So we essentially need to determine the total milliequivalents and then divide that by the volume in liters to find out whether it is more or less. We already have the MEQ for calcium. We don't need to do much there except to add it to the MEQ for phosphate. So that's where the mathematical manipulation is needed. You have 2 MEQ per millimole, right? So let's talk about the phosphate. You have 2 MEQ per millimole. We multiply this by the millimoles of phosphate, so 40 millimoles. This gives you 80 milliequivalents. So the total MEQ is going to be equal to the 80 plus the 20. and that's going to be equal to 100. Now we need to divide this by the volume of the preparation in liters. So all of you could do this by inspection, but let's just talk about the volume in liters. So volume in liters, you have 2100 milliliters, and the conversion factor is 1000 ml, 1 liter. So this is 2.1 liters. What that means is you're going to take the 100 milli equivalents and you're going to divide it by 2.1 liters. And this gives
47.6.
Okay, thank you. So 47.6 MEQ. And you simply compare it to 45. Is it more or is it less? It exceeds it, right? So if it exceeds it, what's likely going to happen?
You're going to have precipitation.
Yes, you're going to have precipitation. It's going to precipitate out. So the learning opportunity here or review opportunity here is, first of all, you want to ensure that all your quantities are in the same unit. So all should be in MEQ like we did for this portion. You want to find the total. And sometimes we kind of like don't really pay attention and we put this answer in the box. That will be incorrect. So you need to divide that by the volume in liters, not milliliters, but rather liters. So you need to either do that in your head or actually convert it on your scratch sheet. Divide the total MEQ by the total volume in liters, and that gives you 47.6 in this example. Since we're talking about MEQ, maybe we can switch to milli equivalents as the next topic. Do just a couple probably, and then switch on to maybe 1 osmolarity, 1 dilution, and then maybe we can call it a day for the review. So this one, I want to make sure that you all have the opportunity to try yourself, and then we'll use this as an example to amplify everything that I think you need to be reminded of for milli equivalent calculations. When we talk about milli equivalents, the one thing we would definitely want to make sure we have completely stenciled on our mind is the equation. Now, what is the equation? Milli equivalents is equal to
milligrams times valence.
Okay. Exactly. I'm happy everybody has memorized that. So normally when it comes to milli equivalents, it's either you're being asked to find MEQ or some concentration of MEQ, so like MEQ per liter, per milliliter, or you're being asked to find the quantity in milligrams, grams, or a concentration. So you could have like a percentage concentration and so on and so forth. But essentially it's either finding this term or that term and doing something with it. The molecular weight is normally going to be given you, or you should be expected to know that one. For example, you should know sodium chloride, right? 58.5. But the one thing that you also need to do is to find the valence. So in this question, one of the things you wanted to highlight is finding the valence. So what we have here is potassium citrate. So it's K3C6H5O7 and it's hydrated. So H2O. Now you're going to put this in water. So it's going to split into a potassium cation and a citrate anion. So C6H5O7. Now this is where you want to pay attention. So normally you have 3 of that, so you need 3 of that, which means your valence here is also going to be -3. So your valence is either the absolute of the charge on the anion, in which case it will be absolute of -3, and then or the absolute of 3 times +1, which is also +3. Either way, the valence is 3. But what you notice is if you incorrectly calculated the valence, then everything else is incorrect, right? So you want to pay attention to that. In most cases, you'll be fine, but just notice the differences depending on what the charges are. So valence is 3. That's important. Now, the next thing that we need is simply to put all of that into the equation, right? What are we looking for? Quantity in grams. So which means we're looking for this term. We have 2 MEQ per milliliter, which means we need to find this term, the total MEQ. So we're going to take this information, 2 milli equivalents per milliliter, multiply that by the total volume, which is 1 liter. And of course, the units need to be consistent. So 1 liter is 1000 milliliters. And this gives you 2000 MEQ. So we can now put in everything back into the equation and solve for our unknown. So here you have 2000 equal to milligrams of a molecular weight, which is 324, times valence, which is 3. So milligrams is equal to 2000 times 324 divided by 3. This is equal to 216,000 milligrams. But we need to be in grams. So you're going to multiply this by the conversion factor that 1000 milligrams is 1 gram. Milligrams cancel out. You end up with 216. So if you did your valence incorrectly, you'd be about 3 times like more than what is needed. What's the important point here? First of all, we just make sure that we completely recall the equation because that's important. On top of that, we review the valence. So generally speaking, your valence is either going to be 1, 2, or 3. And most of the time, you can quickly determine that. Now, in this scenario, I just put in this potassium citrate will have a valence of 3 because the valence of citrate is -3, and you need 3 charges of potassium to balance that out. So whether you're using the cation or the anion, it's always going to be the absolute of the charge on either of them, not adding them, subtracting them. Just pick one. If you prefer to use cation, then in this case it will be 3 times +1. Absolute of that is also going to be 3. Or if you like to use the anion, just find the absolute of -3 is also 3. So having done the valence in this question, because of how it's framed, you want to find the total MEQ and then you set it up and then do the conversion at the end. So I'm comfortable and confident that you are confident and comfortable to do this type of questions. It's just the application and being intentional when we are solving the question that we want to practice.
I have a question. So we shouldn't just memorize once in the book, just the 1 and the 2.
You just can't memorize.
The book gave us like a table of a few compounds.
Of the compound, yes. If you want to memorize the compounds, you can do that. I don't recall exactly what the book showed, but give me an example of what the book said.
For like ammonium chloride, potassium chloride.
Yes, you can memorize those if you want to.
All those have like valence of 1.
Yeah, so and that would be correct. And so it may or may not have had potassium citrate in there. If you can memorize all of them, you can, but honestly, there's no real. You could do that as an approach, but an approach that you will never forget is if you know what all the cations are. Let me give you an example. So let me explain what I mean a little bit. They are essentially lithium, potassium, magnesium, aluminum, calcium. I believe these are the 5 main cations you're actually likely going to deal with. So whenever you have a situation, just pull out the cation. So in this example, let me just illustrate with this example again. So let's say you didn't know anything about the valence at this point in time, and you had K3C6H5O7H2. The water always goes with water. Now what you do is, even if you don't know anything about the compound, just pull out the cation. It's a potassium cation. Ideally, it should have a charge of +1. Because you see there's a 3 in the subscript, it means you have 3 of that. And what that will mean is, even if you didn't know what the anion is, you simply put all of that together. So I'm going to do that at the bottom. So C6H5O7. It needs to have 3 minus to balance these 3 positive charges. So you can memorize all the compounds in the book if you want to, or if you're looking for another strategy, just understand that these are the cations you're likely going to see and know what their charges are. And when you see them in the compound, just pull them out. So let's do a few examples to reinforce that. Lithium is +1, potassium is +1, magnesium +2, calcium +2, aluminum +3. Those are the 5 that you ever need. So let's look at yeah.
Dr. Before you move on,
yes.
Why here, like I put in my notes, potassium citrate?
Yes.
Because I didn't look at the formula. So I just thought about the potassium and I said +1, but that was a mistake. How do I not make that mistake? Yeah. I just...
So honestly speaking, what's going to happen is whenever you have the compound, you should know what the formula is. You can't just go based on the way. If you're going based on the way, it means you know what the formula is from past experience. So if it's not given you, if it says sodium chloride, it's most likely they're not going to put NaCl there because the expectation is you know it. Magnesium sulfate, you should probably know that. But the ones that are less obvious, they are more likely going to give the molecular formula. And that's when you want to use this. I mean, many people don't talk about it, but you want to use a strategy like this.
Got it. So we look at the number right next to the potassium. So it will be 3 times 1. Got it.
Yes,
thank you.
Exactly. So just to emphasize that, because I think that's important, and I think there was a question on that. Let's do a few examples to reinforce that. So if I said lithium carbonate, right, and I don't give you a molecular formula, I don't know whether that's good for you or bad for you. Don't say anything, right? But if we said it was Li2CO3, you should be able to tell what the valence is going to be. So from here, we said lithium has a charge of +1. We are only memorizing. If you want my strategy, which I can recommend highly because you will never get it wrong, is you just memorize those 5 cations. So lithium has a charge of +1. So I know that for sure. I see a CO3. I don't know what the charge is. It doesn't matter to me. because I know my cations. My cations, I really know them. So Li plus 1, but there are 2 of that. So just put a 2 there. These compounds need to be neutral. So if I have 2 times 1, which is 2 positive charges, this one right here should be 2 minus. And actually for the valence, it doesn't even matter. If you're balancing the equation, that's fine. But here, you simply can take 2 times plus 1. So your valence is going to be the absolute of 2, or positive 2, which is 2. If you like to use your cations, it's going to be absolute of negative 2, which is 2. If you are having issues with the anion part, because that is where you have acetate and citrate, and sometimes they have longer molecular formulas, just stick with the cation. But understand that if you have like a subscript here, that will be your stoichiometric coefficient on this side as well. So that was that example. Let's take another example. Let's say magnesium sulfate. So I'm just going to put the molecular formula there. What's the charge here? I mean, what's the valence?
Magnesium is 2 plus.
Exactly. Magnesium is 2 plus. I mean, I like to put everything down because, you know, I'm very particular. But if you were just looking for valence, you know your magnesium is 2 plus. There's no subscript. Valence is 2. Magnesium chloride. What's the valence?
Magnesium 2 plus.
Yeah. So if you want to go all thing is magnesium is 2 plus. There's no subscript. So that means you have chloride minus, you have 2 of that. But valence is 2. If you want, just stick with the cation. So let's do another one. Let's do aluminum hydroxide. What is the valence of aluminum?
3 plus.
3 plus. Is there a subscript? No. So there's nothing here. So valence is 3. Believe me, if you know your 5 cations, I mean the charges on them, and they're either 1, 2, or 3 anyway. The only one that is 3 is aluminum. Everything else is 2 or 1. So if you know that, just pull out the cation, whether it's in penicillin G or let me pull out a more complicated one. Because sometimes you would have penicillin something, you know, and it looks like a complicated structure. But if you follow my guidance or what I'm just telling you, you will never get it wrong. So, how many of you have heard of phenytoin?
Mm-hmm.
You heard of phenytoin? Okay, good for you.
Let me see the formula.
Let's see the formula. Okay, so if I just said phenytoin, it wouldn't help much, right? But if I add the sodium to it, so phenytoin sodium has this formula: C15H11 N2 NaO2. What is the valence?
Pull out the sodium.
Pull out the sodium. Yes. Is there a number next to it?
No.
So what's the valence?
Plus 1.
That's it. You're done. I mean, you could go ahead and write out everything else, which would be your anion. So let's see, C15, H11, and 2O2 minus. That's what that would be. I mean, there's no space here. So if you can pull out your cation and look for a subscript and there's nothing, if there is something, they just put that there and then you multiply that by your cation. That will always be your charge. Let me find one more just to make sure that for once and for all, this thing is settled, and then we move on to another question. But if you do what I'm telling you, you'll never get it wrong.
Thank you for this approach. I always mix up the value.
Yeah. So I know sometimes there's penicillin something, right?
One of those that the exams love to put in the questions.
You know, the disclaimer, I have no idea what the exams love, but I'm sure you love penicillin. So
The ones that they have a trick for you.
yeah, I mean, everything they ask you already have seen before, I'm quite sure, in your study somewhere. But let's see. Penicillin 5 potassium. You've heard about that, right? Penicillin 5 potassium is C16, H17, all of these weird molecules, KN2O6, and then a sulfur. I'm sure if you see this, oh my goodness, what sort of complicated compound is this? Now, what's the valence on this?
1.
Yeah, you see, by inspection. So you just pull out the cation 1, there's nothing else, the valence is 1. So it doesn't matter how complicated this thing looks, the valence is, it is what it is. Yeah, so this question I actually put there because you know what to do, but sometimes I think we need to talk about it. Okay, let's discuss. Now, let's talk about what the question is. It's a fairly short preamble, so it's asking for percentage concentration. What is the percentage concentration of a solution that contains 200 milliequivalents of magnesium sulfate per liter? Round to nearest 10, do not include units, and so on and so forth. So, how do you approach this? You start off with the equation. Milliequivalents equals milligrams per molecular weight times the valence. But how do you get percentage concentration? Can anybody kind of give us a path to get into percentage concentration from this equation?
Well, you need grams on mils.
Yeah, so basically a good step is to find grams in volume, right? So to make things a little bit, just so we are aware that we are dealing on a per liter basis, we can divide both sides of the equation by a liter. So you have MEQ per liter and milligrams per liter. Actually, let me rewrite the whole thing here. So MEQ per liter equals milligrams per liter divided by molecular weight times valence. Now, the main reason I write it this way so that we don't forget that we are on a per liter basis, because sometimes, you may forget. So what that means is we have 200 MEQ per liter. So that's okay for the left-hand side. We are looking for this term, and then we'll manipulate it to get to our percentage concentration. We have molecular weight, so we need valence. Yeah, valence is 2. Yeah. So magnesium sulfate, you put that in water, you have a magnesium cation, there are no substrates, you have a sulfate anion. You can find the valence on either the charge on the cation or the anion. So valence is absolute of +2, which is 2, or of -2, which is also 2. So we figure that out. So now we just need to substitute everything into the equation. So we have 200 equals milligrams per liter divided by 120 times 2. It implies that milligrams per liter is equal to 200 times 120 divided by 2. That gives something, I guess. Let's see, calculator.
1,200.
1,200?
5,000 or 1,200. 12,000.
12,000? Okay, 12,000 milligrams. But this is per liter, right?
Yeah.
Okay, so then the question comes, how do you get to percentage strength from here? So what we need to recall is percentage strength is some quantity in grams out of 100 milliliters. Okay, so definition is grams out of 100 ml. That's important. Grams out of 100 ml. So it may be strategic to convert the milligrams to grams, and then we can set up a proportion later on. So let's just do that. So we're going to take the 12,000 milligrams per liter, convert the grams. So 1,000 milligrams is 1 gram. So we're in grams per liter, and if you prefer to work in milliliters, you can actually convert this. Let's just convert everything to milliliters. So 1 liter is 1,000 milliliters. So now this actually is equal to, so 3 zeros will cancel the 3 zeros. Email the decimal place. Yeah, 0.012 gram per ml. So we can set up a really nice proportion using this information. What we want to say is it implies, okay, we have 0.012 grams in 1 ml. How many grams will be in 100 ml? So this right-hand side of the equal to sign, when we find the x value, that value will be our percentage strength. So let's go ahead and solve for x. X equals 0.012 grams times 100 milliliters divided by 1 ml. That goes away. And this should be 1.2%. Decimal moves 2 places to the right. That gives you 1.2. So although the question is short, it's relying on 2 concepts. It's relying on our understanding of milliequivalents and then synthesizing that understanding with our knowledge on concentrations, which is percentage strength in this example. So you should be able to make the connection. And that's what I meant, that whenever you have MEQ type questions, you're either finding MEQ or you're finding milligrams to find something else. So here we are finding this information to end up to find percentage concentration. It's not a direct link. There are many layovers, but you should be able to connect those in the mind. So if we were stuck, what will we do? Because we've been given MEQ, we will find this quantity, and that will bring us somewhere here. And once we get here, we need to bring in this component. So the reason I'm emphasizing that is when you see a question like this and it looks like you don't know what to do, don't freak out. You know what to do. Just start your process using what you have and what you can determine. At least get to this step. And when you get to this step, you know that percentage concentration is grams out of 100 ml. So now you begin to work on your units. That's why we started off with dimensional analysis. It's a powerful, powerful process. That's what we're doing right here. And that got us to this, and then we can use the understanding. So I wanted to make sure, just remind all of us, we know everything that we should know. We just practicing how to use it. That's where we are right now. And the more we do it, the more informed we'll be for when we take the exams. Okay. Let's do 1, because sometimes they talk about osmolarity. So let's do 1 for osmolarity. Then we can do a dilution. All right, let's talk about osmolarity. So how many grams of calcium chloride should be dissolved in water to make 150 milliliters of solution that contains 596 milliosmoles per liter? First thing we need here is the osmolarity equation, and that states that milliosmoles per liter is equal to quantity of substance in grams per liter divided by molecular weight times
number of particles.
Exactly, number of particles
Times 1,000.
Times 1,000. So we want to keep this at the fore of our mind so that we can use it when we need it. What is number of particles? So let's start off with that. Anyway, let me make a statement here. So this is very similar in terms of thought process when you look at milliequivalents. You can only be asked stuff about what's on the left-hand side, which is osmolarity, milliosmoles per liter osmolarity, or the quantity in grams per some volume. So you could be asked to find grams per liter, grams in 250 ml or something, or you could be asked to find a percentage, but regardless of whichever thing you're being asked, it's either going to be for the left-hand side or this term. The number of particles is also something you need to determine, and let's see how that is different from valence. So in valence, we're looking at the charge. In particles, we're looking at the number of species. So this time it's important that you know how it completely dissociates in water. You have calcium chloride, you have calcium cation, you pull that out, that's a charge of 2+, and then you have your chloride anion, and you have 2 of those. But what you are counting is you have 1 calcium, you have 2 chlorides, so your number of particles is 3. In particles, you count the actual number of species you have. So if we said you have aluminum hydroxide, how many particles does this have? 4. Yeah, you're confident. Say it 4. So it's aluminum 3 plus OH minus, and there are 3 of those. So 1, 2, 3, 4. So you actually count the number of species. Now we found that. Let's proceed with solving the question. What we're going to do is we know the left-hand side because it gives us 596. So we put that there, 596. We are looking for grams per liter. Molecular weight is given as 147. We found our particles to be 3 and you multiply by 1,000. So grams per liter, you do all the algebra math, 596 times 147.
It's divided by 3,000.
Exactly, divided by 3,000 or 3 times 1,000. And what does this give us?
29.2.
29.2, but notice this is grams per liter.
Grams per liter.
Okay. So now the question is asking for how many grams you need to make
150 million.
Yeah, so we need to scale this down. So we could do like a proportion here. So you have 29.2 grams in 1 liter. How many grams do you need in 150 ml? Now 150 ml, you want to convert that to liters, or you can convert the liters to milliliters, doesn't matter. But let's divide, if you divide 150 milliliters by 1,000 ml, you will get 0.15 liters. I didn't kind of show that step, but we are using the information that the 1,000 ml is 1 liter, and that's how we got the 0.15. And we can go ahead and do the manipulation or the algebra. So X is going to be equal to 29.2 grams times 0.15 liters divided by 1 liter. And this is going to be equal to 4.38 grams. So key points to remember: equation, ultra important. Number of particles, determination of number of particles, you want to be proficient in that. You always count the entire species. So when we looked at some of the strategies to deal with milli equivalents in the previous examples, we said you could simply use the cation. For this one, you need to actually write out the entire stoichiometric equation so that you can count the species. I mean, you can do it in your head. You could count from here, 1, 2, 3. That's another strategy, but that's only if you know that works for you and you're comfortable with that approach. Other than that, you can kind of distribute it out and then find the stoichiometry. Now, having said that though, if you wanted to practice this particles a bit, what I use as a trick is you count from the molecular formula itself. So let's say you have magnesium chloride, right? So magnesium chloride, 1, 2, 3. There are 2 of this, 1 of that gives you 3. That's the number of particles. But if you want to be very systematic, then you need to write it out this way. So if that wasn't clear, let me try another one. Let's see, magnesium sulfate, 1 and 2. Let's see, lithium carbonate, 2 lithium, so 1, 2, and 3. That's another way you could do it. But to be very precise, you can kind of put out the stoichiometric equation and then you go through that. Then, of course, once you found the information in this example, sometimes you could be asked to find on a different volume as a percentage. You should be open to connecting those ideas, is what I'm saying. I think that was a good one to summarize all our thoughts on osmolarity. The last thing we will do for this session is to do a dilution question. How much of 100 milligrams per 5 ml product must be mixed with the contents of the 20 milligrams per 5 ml product or morphine sulfate bottle to prepare the desired percentage strength? You have a 1% morphine sulfate solution. You have 120 ml of the morphine sulfate, which has this concentration, and a 240 milliliter bottle of morphine sulfate with this concentration. So what this question is telling us is we are using all of this 120 ml. ml of morphine sulfate. The desired concentration is 1%, so it's good practice just to make things easier to convert everything to percentage strength. So let's start off with the 20 milligrams per 5 ml. So for that concentration, you have 20 milligrams in 5 milliliters. We want to convert this to grams. So 1,000 milligrams is 1 gram. And actually, just for clarity, I'm going to keep it this way. So you have 20 grams in 5,000 milliliters. Let's convert this to concentration. So 20 grams in 5,000 milliliters. To get to concentration is some quantity in grams over 100 ml. If we solve for the x, which is the unknown, that gives us the percentage strength. X is going to be equal to 20 grams times 100 milliliters divided by 5,000. And what does this give us? It gives 0.4%. So this 0.4% is lower than 1. So we have a concentration that is lower than 1. Now we need to find the percentage strength for the other component, which is the 100 milligrams per 5 ml. So we repeat the process actually. So 100 milligrams in 5 milliliters. Let's convert the milligrams to grams. 1,000 milligrams is 1 gram. We keep 100 grams in 5,000 ml. The only reason I'm doing this is because it's easier for the computation. So let's do that here. So 100 grams in 5,000 milliliters should be equal to some quantity in grams over 100. When we solve for y, that will be the value we need for the percentage. So y is going to be equal to 100 grams times 100 milliliters divided by 5,000, and this gives 2. So 2%. So we have 1% that we're looking for, which is our desired concentration. We have 0.4 and we have 2%. Because our desired concentration is between those two, the best approach is to use alligation. So alligation, the higher strength goes to the top left. So that's 2. The bottom left is the lower concentration, 0.4. And in the middle, you have 1. Now on the right hand side, you're going to be finding the number of parts of the 2% and the 0.4%. And the way you do that is to find the number of parts of the 2%. You take the 1, subtract 0.4 from it. That gives you 0.6. So you have 0.6 parts of the 2%. Then to find the number of parts of the 0.4%, you take 2 minus 1. That gives you 1. So you have 1 part of the 0.4%. So now that we have these parts, because we have 120 ml of the 0.4%, we can use the number of parts and that quantity. What that will mean is you have 120 milliliters represented by this 1 part. How many milliliters will be needed for 0.6 parts, which is this one right here? So we solve for the unknown, which is z. And z equals 120 ml times 0.6 divided by 1. And that's going to be equal to 72 milliliters. So I know it's a little bit wordy, but the only reason I brought it is because it allows us to do a number of things. The first thing is to practice the conversion to percentage strengths. And then the next step is to use the alligation method. Okay?
Dr. Demko,
Yes.
can you just use the milligrams per mil, like the 20 milligrams per 5 mil? You just have it like a 4 milligram per mil. You just have that as your strength. Then the 100 milligrams per 5 mil, you have it as a 20 milligram per mil. Then with the 1% morphine, you convert the 1 gram per 100 mil to milligram per mil, which will give you like 10 milligram per mil. So you just use like 20 for our higher strength, or for our lower strength, then 10 in the middle. I think I still came up with 72 mil.
Absolutely. So you can do exactly that. Absolutely. So the important thing is, actually that may be shorter if you are more comfortable with that approach, because everything else is in milligrams per ml. The important thing in alligation on the grid is that the units must be the same. So if you go the route Chantel was describing, which is exactly correct as well, you'll be in milligrams per ml. So just make sure that the percentage is also in milligrams per ml. But you can do that. Absolutely. It's absolutely correct. All right, so hopefully this was a quick review to get us still energized about our preparations for the exams. Hopefully we covered what I think is important things to reinforce. If you have any questions or more questions at any point in time, you can send me an email. I'm normally very responsive to that. So I hope you found this video tutorial useful. If you did, be sure to like it and share it. And if you have any questions, leave them in the comments and I'll get to them as soon as I see them. If you'd like to learn more pharmaceutical calculations, tips, tricks, and strategies, then start by subscribing and clicking the bell so you don't miss anything. Thank you so much for watching, and I'll see you in the next video.